In this lecture, we will talk about radio frequency accelerators. In the earlier lecture, we talked about DC accelerators. Now we talk about radio frequency accelerators. Indeed, to get the highest energies, you have to make use of radio frequencies. So basically, the radio frequency power is applied to electrodes to accelerate particles in phase. So of course, the radio frequency goes through a positive and negative cycle. So you do it in such a way that it always sees the accelerating phase. So you have to have, first of all, a bunched beam, and you have to have the right electrode structure in order to be able to accelerate it, so that it always remains in phase with the accelerating part of the RF. The accelerating structure or the unit can be repeatedly used, as in the cyclotron or in the synchrocyclotron or in the synchrotron. Alternatively, you can, instead of using the same structure, you can have accelerating cavity is repeated, as in a linear accelerator. So you have this particle going through many such cavities, and it gets accelerated at each of the gaps between the cavities, the electrodes in those cavities. Now, in all of this, superconductivity plays a major role. And why is that? So it can do it in two ways. In cyclotrons or synchrotrons, you have magnets which actually help in bending the trajectory of the particle, the charged particle. So there you can have coils which are superconducting coils, so that you save power, and the only power that goes is that is dissipated is in the conductors that come from the power supply to the superconducting coils. And this, by the way, the current can run into kiloamperes or even tens of kiloamperes, as the case may be. In the case of linear accelerators, the cavities themselves could be superconducting, so that you have a tuned cavity to a particular frequency, and what happens is that you apply a very small amount of RF power, and the voltages that are generated in this cavity roughly go like Q times that voltage that you apply. So you can get very high voltages with a very small amount of input power. So this power, in the case of room temperature devices, LINACs, this can run into literally hundreds of kilowatts or even megawatts. Whereas in the superconducting case, these are like hundreds of watts. You have a huge saving. Of course, you have to pay a price for that. You have to have cryogenics to take this cavity to its superconducting state. And so the choice between using normal superconductors, both in terms of cavities in the case of linear accelerators, or in magnets in the case of cyclotrons, synchrotrons, and so on, that depends on the trade-off between the issues regarding handling the cryogenics at liquid helium temperatures or the power budget. So at room temperature, your power budgets are high, but you are not going to, you're operating things at room temperature essentially. Whereas in the case of superconducting cavities or magnets, you are handling cryogenics. So this is a trade-off that the builder has to decide. So recap of lecture 3, the cyclotrons, as we remember, works because if you use the Lorentz force and equate it to the centripetal force mv squared by r, then you get a frequency which is independent of the energy of the particle. And this is so as long as gamma is close to 1. That means in the non-relativistic domain. If that is so, then the frequency is independent of the energy of the particle. Okay. These are the various symbols that are used. So the B rho is equal to square root of kinetic energy squared plus 2 times kinetic energy times the mass. There's a c squared missing, so in this c is assumed to be 1. But really speaking, there should be a c squared if you want to balance the units. Okay, so as the t increases, the B also should increase to keep the particle in phase or on track for a given r. So for instance, in the low energy domain, m is much larger than the kinetic energy, so you can forget about this t squared term, and so P is just given by you know, or proportional to square root of 2Tm. Whereas if you go to the highly relativistic domain, then of course P goes like T or the E, okay, where E is the energy of the particle. So again, a recap for the synchrotrons. Cyclotrons have this limitation that the maximum energy is of the order of 1 GeV, because of course when you go to higher and higher energies, the magnetic field has to be tuned so that it remains in phase. Okay, so you have to increase the magnetic field due to the relativistic effect. And of course, as you go to higher and higher energies, the magnet cost increases because it goes like dimension cubed. Okay, so one solution that was found by Macmillan in 45 and independently by Wechsler in 44 in Russia, in the then USSR, was to actually take out the full magnet and just have one ring of magnets. The price that you have to pay is, of course, that this pulsed machine takes these pulses, and as the energy increases, you have to increase the frequency or the magnetic field, both of them. Okay. Of course, once it becomes relativistic, then the frequency rise is not there. You only have to keep increasing the magnetic field. And so it takes about of the order of a few seconds or 10 seconds to accelerate it to the highest energies. Then you take the the accelerated beam pulses out, and then you start this cycle all over again. So this has a relatively low duty cycle. So the useful beam versus the total time taken to accelerate, this is a smaller fraction, whereas from a cyclotron you could get beam continuously in bursts, but then you can go to very high energies. And so this is the beauty of the synchrotron. There is an important aspect which is discussed by Macmillan in his PhysRev paper, which talks about the synchrotron, and namely the question of phase stability. So if you are on the accelerating part of the RF cycle and you take a reference defined by, let's say, the blue dot here. By the way, this figure is taken from the PhD thesis of Dr. B. Srinivasan. So a particle that is arriving early is accelerated less, and then it arrives a little later. Similarly, a particle that arrives later is accelerated more, and it comes earlier. So this role is interchanged in cycles, subsequent cycles. So this particle actually is said to perform betatron oscillation about the mean phase, and this is the principle of phase stability. So if a particle is slightly out of phase here, it goes up in phase and then comes down and so on. So it hovers around the central phase. So this is the principle of phase stability in RF accelerator. This is true for synchrotrons, for also linear accelerators. All of these RF accelerators, this principle of phase stability is central. Provided, of course, you operate at the right phase. The central part is to operate in this phase. Okay. If you operate in this phase, then particles actually move out. This has another consequence, namely you can get energy bunch beams, but we will not talk about that here. I want to only talk about phase stability here. So again, doing a recap, the synchrocyclotron is a modification of the cyclotron. What you do is you have only one D, and cyclotron of course has two Ds, where the particle gets accelerated in between these two Ds. So, but apart from that, as the particle moves out, the frequency can be decreased. So this is again not a CW machine like the cyclotron, but you have to operate it in pulses. So for some period when the frequency is increasing, that beam bunch is getting accelerated, and of course things don't happen right at smaller radii. Okay, so this is but you can get fairly high energies, and in fact the first accelerator at the CERN machine in Geneva was actually a 600 MeV proton synchrocyclotron. And there were several at that time. There was one in IP and Orsay, one elsewhere. I mean, there were several elsewhere. So the D voltage can be lower, of course, because you are actually taking the pulse and accelerating it. So the voltages that you have to apply are smaller, and so on. There is a patent on this of Macmillan, the same gentleman who invented the uh, principle of the synchrotron, and this is the 1952 patent. In a linear accelerator, you accelerate the particles in a linear fashion. So, what happens is that you have a particle that, let us say an electron in this case, but you can also have a proton with the opposite phase, then this would be minus, this would be plus, but let us consider the figure as it is. So, in this case, electron is produced from an ion source, and then when it comes to this gap, it gets repelled by the negative voltage here, attracted by the positive voltage, so it gets accelerated. By the time it drifts through this electrode, it again sees a accelerating voltage, and so it keeps on accelerating. Okay, so that's how you get a you know acceleration of the particle. So so, in this case, when the RF is applied, if this is positive, then this electrode is negative, but in the second half of the cycle, this will become negative and vice versa. So, you can arrange it such that the particle is always accelerated as long as it comes in phase. And so, this structure where as it gets accelerated, of course, its velocity increases. So, the length of the drift tube also has to increase correspondingly. This is called an Alvarez structure. So, as the energy increases, the length of this electrode has to increase. The phase stability, of course, applies as in the case of the synchrotron, indeed any device. So, this is shown a little better here, where let us say you have a RF cycle where this is negative and this is positive. So, the particle gets accelerated. In the next half of the cycle, this becomes negative and this becomes positive. So, the electron, let us say, is again accelerated here, and its velocity increases. So, you have to have a slightly longer electrode, and then the same thing continues. Okay. So, these are pictures of Linacs. This is the Alvarez drift tube Linac. These are all copper because, of course, copper is the best conductor that we have, and that is so even for RF. This is a room temperature device, but and this is the old Linac picture. The new Linac, of course, is like this here, and that most of modern Linacs, of course, will use superconducting cavities. Now, once you have accelerated the beam, then you can put it on a target, and then you can produce whatever reactions you want. There is a problem. If you want to go to higher and higher center of mass energies, it turns out that because of relativity, the energy in the center of mass frame only goes as square root of the energy in the lab, essentially. Okay. So, most of the rest of the energy actually goes in moving the center of mass. Now, if you want to go to the full energy of the beam, then you have to actually collide it. So, instead of having a stationary target, you have to have a beam moving in the opposite direction, and so you have to have colliding beams. And of course, if you have a storage ring in which you store these colliding beams, you can increase the number of times this collides, and that it has many more chances of interacting with its counterpart. So, let us consider, let us say, this, of course, we have gone through this once, I think, in the earlier lecture, but let me go through this again to show the root E dependence. So, the energy in the center of mass is given by this expression, m1 squared plus m2 squared plus 2e1 lab times m2 square root of that, where m1 is the projectile, m2 is the target mass. This is the beta, the velocity of the center of mass with respect to velocity of light. This is just given by P1 lab by E1 lab plus M2. The gamma factor, which is related to beta, inverse of square root of 1 minus beta squared, is given by this expression, E1 lab plus M2 divided by ECM. And you can see that the energy in the center of mass is for much larger energy that compared to the masses of the interacting particles, then essentially this just goes as square root of, proportional to square root of E1 lab. So, for example, if you take a 1 TeV proton on a stationary proton at rest in the lab, then you only have 32 GeV to produce various new particles and so on. So, if you want to create massive particles, you have lost most of the energy that you accelerated the particle to. And so, that is where the need for colliding beams comes in. So, of course, when you have colliding beams, then the luminosity is much less than that of a fixed target. So, you have in a fixed target, you have about 10 to the 21 atoms per square centimeter, whereas if you have a beam, you only have about 10 to the 12 particles per second, corresponding to, let's say, a fraction of a microampere. But of course, you can focus these beams. So, you can make them, in fact, to sizes of the order of tens of nanometers to a micrometer, and therefore, you can get luminosities which are of the order of 10 to the 33 to 35 per square centimeter per second. Okay, we have already defined luminosity in an earlier lecture. So, basically this tells you that if you have a certain cross section, then how long would it take to get a certain event rate. So, for instance, if you have LHC which is designed to have 10 to the 34 centimeter minus 2 per second, then the event rate for a nanobarn is of the order of 10 per second. So, this you can very quickly estimate for a given luminosity, and for a certain cross section what would be the event rate. Okay. So, circular colliders for electrons and positrons, as happened in the case of the uh, large electron positron collider, which resided in the same tunnel, 27-kilometer circumference tunnel at CERN, where now the LHC resides. This was limited to about 100 GeV. I mean, they went slightly higher than that, I think up to 110 GeV or so. But then at the highest energies, you get radiation loss. So, the energy of the electron positrons damps because of synchrotron radiation. Also, due to beam interactions, you have losses, and these actually increases e to the 4. So, it is a very high power of E. So, you can't go much beyond this 100 GeV or so. Linear colliders bypass this problem, because you can have an electron positron colliding and it is moving in a straight line. So, there is no acceleration. I mean, the small amount of acceleration that is there when you accelerate it in a LINAC, that does not lead to such a heavy energy loss. So, however, the problem is that this is a single pass machine. Okay. So, in a single pass machine, of course, there is a lot of energy in the beams. So, you have to devise methods of recovering the energy in these beams and then going through the whole process again. Also, because it is linear, the accelerator is long. So, for a TeV energy, for instance, you require something like a 10-kilometer long uh, machine. You have to focus it. For instance, in the Stanford Linear Collider, the focusing was of the order of micrometers. So, about 2.6 in the case of X and 1.2 micrometer in the case of Y. KEK has achieved even better. This is an old figure. They have gone down to even hundreds of nanometers, so fractions of micrometers in each of these dimensions. So, but these are things that are done. You can focus the beam, and therefore you can improve the luminosity, because the luminosity, of course, is inversely proportional to the cross sections of these beams. Now, of course, when you have these beams, you would like to store them, and this is done, for instance, in heavy ion beams such as the ESR ring in the GSI, where for instance, there is an example of that. There is a picture of that. There is a picture of that ESR storage ring. Circumference is about 100 meters or so. B rho max is this. So, you can store very heavy ions circulating in this, and you can make mass measurements. You can even cool the beam. You have an internal gas target, and the overall vacuum in this is of the order of 10 to the minus 11 millibar. And this has been extensively used to make mass measurements of nuclei which are produced in the accelerator that is there at GSI, for which are very much off the stability line. So, these storage rings, of course, where you have to first take the accelerated beam and then cool it, either a electron, proton, or heavy ion beam, and you can do cooling of this by either stochastically, as was done by Simon van der Meer, or by electron beams. This is a faster method of cooling. So, you have a co-moving electron beam which has the same velocity of the beam, that the central velocity of the beam that you want to cool, and then the beam particles share energy with the electrons and they transfer their quote unquote heat to the electron beam, and the electron beam is very easy to produce. So it comes back and then you can produce it again with a very sharp velocity spread, and so this way you can cool it using a co-moving electron beam. There is a third method of cooling which is called ionization cooling, and this is still not a method that is used in accelerators, but the proof of principle has been done. This is useful when you want to cool beams on a very short time scale of the order of microseconds. For instance, this has been conceived in the context of cooling muons which come out of the decay of pions. So these are second order secondary beams, and they might be useful in making muon colliders, for example. And since the muon lives only for 2.2 microseconds, even if it is relativistic, if a gamma factor of let's say 100, still that means about 200 microseconds. So you have to do everything within 200 microseconds. So so you have to cool it, accelerate it within a very short time, and that is where this ionization cooling has been conceived, and this has actually been proof of principle has been done. The other place where storage rings are used, of course, in synchrotron radiation sources, where you have beams of electrons, or sometimes in some cases they also use positrons. So for instance, you have this stored and it has lifetimes of the order of a few to 24 hours. This is a machine in Japan, Spring 8, and in Indus 2 in Indore, this was surviving for about a few hours. I think that has now increased to about 12 hours or even more. And the advantage of this storage ring is, of course, that you can use the same beam many times to produce secondary beams of interest or making collisions and so on. And you can have rather low beam bunch intensities. You can still carry out experiments. You can have internal gas targets for very high energy resolution and so on once you have these cooled beams circulating in them. The future of course, high current machines, when you want to produce secondary beams such as muons and so on, or second order secondary beams of muons, is the so-called fixed field alternating gradient accelerator. It is actually a modified cyclotron, but with very large aperture magnets, and also very large aperture both in terms of X and Y. So the cross section is, for instance, shown here. This is a picture of prototype proton, so-called fixed field alternating gradient accelerator at KEK 2001. The original proposal was way back in 1956. Simon, I think he was at Lawrence Berkeley at that time. So the idea is that it has a large longitudinal and transverse momentum acceptance, as would be there for secondary beams also, and it would be strong focusing because it's alternate gradient. So you have gradients which are opposing one another. So one focuses, the other defocuses, but overall you get a focusing effect. You have fast acceleration because it is fixed field. It is not like a synchrotron where the field is being ramped up, and it is important in producing secondary beams such as the pion. So originally this thing would be used for protons, but as a proof of principle, of course, it can be used for other beams as well once the proof of principle is shown. And to my mind, I think this has in principle been shown. And then there are again two kinds of FFAGs, where you have a magnetic field which goes like a power of radius. That way you can avoid certain resonances that take place which take away the beam. But you can have non-scaling ones, and I think this is the one which is more popular, where the field decreases at the higher R for some sectors, increases for some other sectors. So this is like an alternating gradient synchrotron. So you have focusing and defocusing, but overall you can have focusing. So you have very high beam intensities possible, and if acceleration is fast enough, even these betatron oscillations are avoided. Okay, so finally we come to very futuristic possibilities of very high gradient accelerators. All these accelerators are running into tens of kilometers for the highest energies. In the case of, I mean, people are even talking about going forward from the LHC to make a machine which has a center of mass energy of the order of 100 TeV, but then that machine would be of the order of 100 kilometers in in dimension. So you would have a ring, synchrotron ring, which has a circumference of the order of a few hundred kilometers. Now, at some point, you have to change this technology. So, one attempt to do that, and again, this idea looks very promising, is to use very high power lasers to produce a very high electric field. This can be done either in nanostructures, up to about 3.5 GeV per meter, you can get there, or you can do it in a plasma where you can get much higher electric fields, much higher voltage gradients of the order of even up to 100 gigavolt per meter. So, imagine you have an accelerator which can produce 100 GeV beam within just a meter or so. This is like a tabletop. So, this helps when you want to go to, let us say, 100 TeV, because then you would just require a kilometer long accelerator. So, an example of such an experiment to prove that this is the right direction to go was, this experiment was reported in 2024. This is the reference, Pixley et al., where they showed that they could produce electrons accelerated to about 7 to 9 GeV, the total charge being about a few picocoulombs over time scales of the order of a few nanoseconds, and over about 30 centimeters in hydrogen, which is spiked with 1% of nitrogen over a smaller distance. And this is done using the laser called Bella, whose power is of the order of 500 terawatt and delivers an energy of the order of 20 joules. So, these are plots that are shown here where they have tried hydrogen, pure hydrogen. There you can't apparently get these kind of accelerations of electrons. If you put in a little bit of nitrogen, then you see some hint of acceleration. If you put over a smaller distance, nitrogen over a smaller distance, then you get a beam which is accelerated to about a little more, about 8.5 GeV or so. And if you, this percentage is over, I think it is, these are for different cases, 3 picocoulomb, 6 picocoulomb, and various charges, then you can get acceleration of up to about 8 GeV or so. If you go to higher percentage of nitrogen, then the intensity is reduced and the energy is accelerated also reduced. Okay. So, they have shown in principle that you can get of the order of 10 GeV electrons with about few picocoulomb charge, which is quite good over a very short time scale. And so, kind of proof of principle is in the right direction, and possibly in future we will have access to very compact laser plasma accelerators to go to still higher energies. So, in summary, I would say that we have talked about major RF accelerators, cyclotron, synchrocyclotron and synchrotron. Then we have talked about a little deeper into linear accelerators, then to colliders, storage rings, and one kind of accelerator for the future, namely the laser plasma accelerator, which could take us to even higher energies rather than just building bigger and bigger synchrotrons. Thank you.